Hello and welcome back to my YouTube channel. Today we'll be talking about discontinuity and continuity. So if we look at this first question here, it asks us to find the type of discontinuity and where it is located. So if we can first factor, we get x minus 5 on top divided by x minus 5 on the bottom times, we'll factor it out to x minus 2. So that whatever cancels is your whole, right? So there's a, so you have to set it equal to 0 first, right? So x minus 5 is equal to 0. So then there's a whole that's x equal to 5. Awesome. And then whatever's left in your denominator is your vertical asymptote. So then x minus 2 equal to 0, x equal to 2. So and then there's also a vertical asymptote at x equal to 2. And this is your answer for this first question, as I was asking for it. The whole and the vertical asymptote. Awesome. Now here it's asking for the same thing, right? So of course, whenever you're working with these types of problems, right, you want to put it in simplest form first. So we can rewrite it as 1 over sine of x minus 2. And again, so at the bottom, whatever is in the bottom equal to 0. We have sine of x minus 2 equal to 0. So we need to find when sine of x is equal to 0. So sine of x over 2 is equal to 0 whenever sine is 0. Based off x, sine cancels. So we have x over 2 equal to 0 times 2 over 1 times 2 over 1. Right? We have x is equal to 0. That's the answer. We also know that sine is equal to x. Sine of x over 2 is equal to 0 at sine of pi. So sine of x over 2 is equal to sine of pi. Sine times 2 over 1 times x over 2 to get rid of that 2. Pi times 2 over 1. So x is equal to 2. So the discontinuities are located at x is equal to 0 and x equal to 2 pi. Okay, moving on. This question asks us to state whether the function is continuous at the given x values and to justify our answers. Okay, so first, x is equal to negative 1. We can look at it negatively. So if you look at the limit of f of x as x approaches negative 1 negatively equals 2. 1 over negative 1 plus 4, which is equal to 1/3. Awesome. And then really, if you look at it from the positive side, limit of f of x as x approaches negative 1 positively, this equals to the negative 1, which is equal to 1/3. So now we know that the limit does exist because negatively and positive reaches the same point. And since here we have a equal to symbol, that means that it all works because f of negative 1 is equal to 1/3. We did the math upstairs. So then, yes, it is continuous because f of negative 1 is equal to the limit of f of x as x approaches negative 1. And that is your answer right here. Awesome. Let's see if I can fit this here somewhere. Continuous at x is equal to 2. If we look at x is equal to 2, do the same thing. Limit of f of x as x approaches 2 negatively is equal to 3 squared, which is equal to 9. Okay, and the limit of f of x as x approaches 2 positively is equal to, we're using the last equation, so 2 squared minus 1, which is equal to 3. And since 9 does not equal 3, then no. It is not continuous because the limit of f of x as x approaches 2 does not exist. And that is your answer for part B of the question. Okay, awesome. Moving on. This question asks us to identify each type of continuity and where they are located, right? Okay. So first thing we're going to do is solve for the negative ones, right? So same process. The limit of f of x as x approaches negative 1 negatively is equal to 2 times negative 1 plus 1, which is equal to negative 1. And then we have the limit of f of x as x approaches negative 1 positively equal to negative 1 squared minus 6, negative 1 minus 6, which in the end we get negative 1 also. But then, so that means that the limit of f of x is negative 1, right? As x approaches negative 1, it's negative 1. That's the limit. But we have here that when x is negative 1, in reality, the answer is 3, right? Y value is 3. So then we know that there's a hole at x is equal to 1. Oh. Hole at x equal to negative 1, sorry. There's a hole there in the growth function. So it's just going to look something like this. So there'll be a graph. And then for some reason when it comes down here, there's a hole. And the actual dot's up here at 3. Right? So that's what we're seeing right there. That's what they're explaining. Awesome. But then we also have to solve for 1. So we do the same process again. So the limit of f of x as x approaches 1 negatively is equal to negative 1 squared minus 6, 1 minus 6, which is going to give us negative 11. And the limit of f of x as x approaches 1 positively is equal to, it's just 3. And since negative 11 does not equal to 3, then there is a jump at x is equal to 1. And what's going on in this function is that whenever x approaches negatively, right, 1 negatively, it's somewhere way down here, right, at negative 11. So when it's coming from this way, it's down here. And it's coming positively, it's up here at 3. So there's positively and negatively. That's what's going on there. But in the end, yes, this is the answer you're looking for. a hole at x is equal to 1, and a jump at 1 at x is equal to 1. Okay, next question. This question asks us to confirm continuity over an interval. So this is fun, and these involve rules. So the first rule is that anything in the denominator cannot be equal to 0. So 5 minus square root of x cannot be equal to 0. So just algebra problem, -5, negative square root of x is equal to -5. The negatives cancel, right? So now we have the square root of x equal to 5. Well, cannot be equal to 5, sorry. We square it on each side to get rid of it. Then we have the x is equal to 25. There we go. And then the other rule is that anything under an even radical has to be greater than or equal to 0. So in this example, square root of x, right? So that means that x needs to be greater than or equal to 0. We have that no. Okay. So then so knowing that we have these two domains, like these two limits, the domain will be x is greater than or equal to 0 until 25, not including 25, union 25 all the way to infinity. And that is the domain for this equation. Awesome. This question asks, which of the following functions are continuous on the intervals 1 and 6? Okay. So the intervals 1 and 6. So let's sub in 4, right? Let's just say, okay, between 1 and 6, x can be equal to 4, right? Okay. So if we do that, sorry, we can get, for this first one, we would get 4 minus 4 divided by 4 squared minus 16, which is equal to 0, divided by 16 minus 16, which is equal to 0 divided by 0. Does not give you an answer. Does not exist, right? Okay, so anyone that has a 1 is not true, right? Because 1 does not give you the answer. So if this is wrong, that's wrong. So now really all we have to do is solve for the second one. So if we have, instead plug in 4 again, we have 4 minus 4 divided by 4 squared plus 16 this time. 0 divided by 16 plus 16, which is equal to 0 divided by 32. That's equal to 0, which is an answer. So we know that, okay, 2 works. Now add natural log of 1 over 4. If we put this into a calculator, we get a number that's not 0, right? So a number greater than 0 that can just be assumed, or equal to 0. So then we can say that definitely 2 and 3, functions 2 and 3 are continuous on the interval between 1 and positive, between when x is less than 1, when x is greater than 1 but less than 6. Sorry. Thank you for your time, and good luck with continuities and discontinuities over this time. Thank you.